So our topic at hand today is oxygen sensor testing and repair. And I know there's certain things with oxygen sensors that can be a little confusing. One works one way, one works the other way, different types of sensors. Also, how do they relate to vehicle drivability and issues such as that? So we're going to talk about a lot of that in this session. So first off, let's talk about fuel trims and how oxygen sensors relate to fuel trims, because I know fuel trims is often misunderstood as well. So with fuel trim, what we're trying to do is we're trying to keep the air fuel ratio in a vehicle to that 14.7 to 1, or we call it stoichiometric air fuel ratio, right? So most places, especially sea level, you want to see 14.7 parts of air to 1 part of fuel, and that would be a perfect air fuel ratio, and we should burn up all the fuel and use up all the oxygen. Now, the oxygen sensor's role in all this, especially the front oxygen sensor, if we have 2 oxygen sensors in the vehicle, depends on how old the vehicle is. But what it sees is, okay, so the front oxygen sensor, it is reading, and all of a sudden it's reading lean. There's too much air in the exhaust. So what does it do? Well, then it adjusts it and sends a signal to the computer and says, hey, I need more fuel to make up for I have too much oxygen. So then it gives a positive fuel trim number. So if you're too lean, you'll see a positive fuel trim number be adding fuel to the mixture. Then it's going to add fuel and add fuel and add fuel as it goes. And then eventually that front oxygen sensor is going to say, whoa, now we're too rich. We have too much fuel. So then it sends a signal over and it says, well, we got to pull back on that fuel. We got to subtract the amount of fuel going in there. So we get what we call a negative fuel trim. So it's pulling the fuel back away. And then it's going to pull it back, and it's going to eventually pull it back too much. And then it's too lean. And then it adds fuel to it, positive fuel trim. Then it's too rich, and so on and so forth in a closed loop. That's where you get the term closed loop fuel control from as well, because it's just going to loop around and move back and forth. And older vehicles, it takes a little longer to kind of move everything back and forth. And then newer vehicles, it's a lot easier to adjust, especially with the newer AF sensors that are out there. So it can adjust a lot more rapidly. And we also have a larger range what's tolerable in there. So if we think about the relationship of oxygen sensors to fuel trim. So I have my oxygen sensor, as we said, the front oxygen sensor. It's going to read rich or lean, and that is going to tell the short-term fuel trim what to do. So short-term fuel trim is going to be, here's what's happening right now. So either I need to add fuel right now, positive fuel trim, or I need to subtract fuel trim right now, which is a negative fuel trim. And then over time, as that short-term fuel trim adjusts, let's say it's like positive 10% for a long time, whatever that period of time happens to be. Then it will make that long-term fuel trim creep up over time. So if I have a lot of long-term or a lot of short-term fuel trim and a positive, it's going to bring that long-term fuel trim to a positive. Then eventually it gets to a point and say, oh, well, I guess this is how the vehicle's operating now. Then the short-term fuel trim kind of backs off and then goes to a neutral state and then adjusts according to where the vehicle is running. So you can use the long-term fuel trim to see, well, how's this vehicle been running over time? And then short-term fuel trim is how's that vehicle running right now. So if you get a 171 or a 174, rich code, lean code, rich code, you can see, has it been going on for a while, or is it just fairly new and it's happening right now? Usually, most of the time, unless it's a massive failure or a big crack or something develops, it's probably going to be a slowly over time working towards that, lack of maintenance, things of that nature. So those are other things we need to work out for. So we have a couple different types of sensors we're going to talk about this evening. The first one's Zirconia sensor, and that's the one that's been around for quite some time. If you think about the single wire sensor way back in the day, I remember, working on Chevys with the single wire sensor. It was right in the front in the manifold there, and it was super easy to get to, and it's super simple in the way it operates, right? You just had one wire, it generates a voltage, sends it down the wire, sends it to the computer, and the computer just does what it needs to do. Newer type sensors are going to look like this. They're going to have 4 wires because they're going to have a signal wire, and then they're going to have a heater circuit in them as well. So you're going to have a power and ground for that. So it allows it to heat up and get to temperature faster. So if we think about a heated zirconia sensor, or even an unheated zirconia sensor, unheated zirconia sensor is going to produce a voltage. A heated zirconia sensor is going to produce a voltage. They both produce voltages. The only difference is that single wire sensor, the older style, is going to require the exhaust, the heat from the exhaust, to get it up to temperature. They want to run around, 640 Fahrenheit or so. That's where they want to be. So takes a little while, especially if it's cold out, to get that exhaust temperature up to temperature where it's hot enough to heat up that sensor. Versus if I have a heater in there, it will increase the amount of temperature that's in there. It'll increase the temperature of the sensor way faster and get it up to that operating temperature where it needs to be. So, like I said, it produces a voltage depending on how much oxygen it senses in the exhaust versus a reference air sample. So you see we have a reference air sample. Now this would be, you can see it on some oxygen sensors if you actually look at them. There are gaps oftentimes around the outside, around the shield there. That allows reference air in onto that one side, on the one side of the membrane. And then we have the membrane inside, which is what creates the voltage. And then we have the exhaust gas on the other side. So based on how much oxygen is here versus what's over there, it's kind of like a differential. It will generate a voltage based upon that differential. It's most accurate between a very narrow band of voltage, which you're going to see on the next screen, about 455 millivolts, which roughly equates to 14.7 to 1, which is roughly halfway between about 0 millivolts to about 900 millivolts, which is the general operating range of a zirconia sensor. As we see how it kind of relates. So a rich air-fuel mixture is going to be up to the high 9s, and a lean air-fuel ratio or too much oxygen is going to go down to about a 10th. And then we see right in here 14.5 and 15.4, kind of somewhere in the middle there, is going to be our 14.7. Accuracy range is positioned between a narrow band of voltage, and that's why you may have heard these called narrow band oxygen sensors, because it's very much a narrow band. And if I were to look at it with a scope, it's going to kind of look like this. It's going to go rich to lean, and rich to lean, and rich to lean, and rich to lean, and back and forth, and so on. Going to kind of move back and forth. Now, there is a rise time set by the manufacturer, what it needs to react. So from it goes to from lean to rich, it needs to react in a certain amount of time, certain number of milliseconds. The manufacturers sometimes publish the spec. But you want to make sure that it rises and falls evenly depending on where your mixture is. The newer kid on the block, I guess, has been around for quite a while, but newer and relative to the zirconia sensors, the AF sensor. Now, usually on most cars that use these, it's going to be the front sensor, and oftentimes you'll have a zirconia sensor in the back to monitor the cats. So air-fuel ratio sensor is going to react a lot quicker, and it also is able to operate in a much wider range and be more accurate in a much wider range. So they've also been called planar sensors, linear sensors, broadband sensors, wideband, or lean air-fuel ratio sensors. Each of those roughly the same thing. So it's kind of 6 of 1. So there's an air-fuel ratio sensor. You see it looks an awful lot like an oxygen sensor because, well, it is. And you see that little gap right there. That allows that outside air to get in. It's going to be very similar to your zirconia sensor. And also similar to your zirconia sensors, we have the reference air. We have a zirconia membrane, but it's actually 2 zirconia membranes sandwiched together with a little bit of a gap in between. And then we have our exhaust gas on the other side. So this works in a fashion of like 2 zirconia sensors mashed together like a sandwich. So I have my reference air out there. These almost always are going to come with a heater. And what it's going to try to do is it's going to be using this voltage. It is going to be trying to get this chamber in here to a lambda of 1. So lambda of 1 is equal to 14.7 to 1. So stoichiometric air-fuel ratio, right? So we'll see that in there. And it does this by taking that exhaust gas and moving it through this membrane. And it varies the current going through this membrane. It's got a little bit of a gap in between. So it allows oxygen molecules in or out of that cell to make it richer or leaner in there, trying to get it to that 14.701 in the middle. So the current can either go positive or negative. Now, you can't really measure the current in there. It's very small microcurrents that go back and forth. The computer actually does all the calculations within and spits out PID data for it. So that's how we're going to diagnose these types of sensors. You're really not going to be able to use a scope for it, maybe the heater circuit, but certainly not for the signal circuit. So it pumps it back and forth, moves it back and forth. So like I said, it's two cells mated together in a planar form. Air-fuel ratio sensor uses an entirely different operating strategy than a conventional zirconia sensor. It actually works opposite to how our zirconia is. So as I said, one cell is going to be used to measure the content in the exhaust stream. The other one is supplied with a very small electric current from the PCM, enable it to move oxygen ions in a positive or negative direction, depending on whether the current goes positive or negative. It's going to give a stoichiometric ratio between both cells, also known as a pumping cell there. And the air-fuel ratio sensor operates at about double what a standard zirconia sensor operates at. So it's about 1200 degrees Fahrenheit versus 640 degrees for a traditional zirconia sensor. And then here's a little animation of how that would work, right? So it's going to move oxygen ions in and out of that chamber back and forth. Going to try and keep it at about that 0.455 millivolts coming out of that cell. And in order to keep it at that 0.455 millivolts, it's going to change the amount of current flowing through this pump cell, either a positive or negative current, to allow that to flow back and forth. So it tries very hard to get that where it needs to be. So as the PCM itself monitors the varying current, the PCM converts the current into a voltage value PID. So you'll often see AFR voltage. The best way to test an AFR sensor signal is by monitoring the actual voltage PID. It is possible to monitor the sensor varying current, but it's very, very small, low milliamp range, like I said, and very difficult to monitor. You'd almost have to break the circuit, and at that point, you're not doing anybody any good at that point because a low amp probe won't be able to read. So you can't really read it in line. It's going to change the circuit. So by doing that, like I said, we want to read the voltage. So lambda voltage or lean air fuel ratio voltage versus air fuel ratio, and then what the OBD2 voltage spit out voltage PID would be. And then we can see how that reacts over here. So like I said, it is the opposite of how a traditional zirconia sensor works, though. And this I know I always have a challenge keeping this in my head, which way is which. So we're going to have a pretty good graphic on the next screen. Actually took some PIDs and leaned out a vehicle so we can see how they react. But when the fuel mixture becomes richer, the voltage should decrease on the AF sensor. Under lean conditions, the voltage should increase on the AF sensor, and then it's going to be opposite. So rich on the zirconia sensor is going to go up, and lean on the zirconia sensor is going to go down. So they work opposite of each other. One good way to view that is here. So this is a test that I did on my own vehicle. So this is it's got a zirconia sensor in the rear behind the cat, and it's got an AF sensor in the front, and right off the exhaust before the cap. Also, since this is a Subaru, so on Subaru, they don't call it short-term fuel trim. They actually call it correction. And then long-term fuel trim is called learning. So air fuel correction and air fuel learning. So that's my short-term fuel trim, and that's my long-term fuel trim. So what we did is I monitored the PIDs while introducing a lean condition. So I took the big fat hose that goes to the brake booster, cracked it off the end of the intake so the vehicle would keep running, but it was introducing additional air in there, introduced a vacuum leak, and then it ended up going lean. So we can see fairly quickly, you can see that's fairly flat around 1. And then we can see fairly quickly as I opened it, that front AF sensor reacted pretty quick to a lean condition. So it started going up to lean. And then you'll notice how the rear oxygen sensor took a little bit longer. A bit of a gap there. That's just because of the distance, mainly. It's the front sensor to the back sensor. That's a few feet, and the exhaust takes a little while to get there, and the oxygen content takes a little while to change. So that's going to happen. We want to see that. Actually, we want to see it react first. The front one react first, and the back one react second, because if it's the opposite, then we have a problem. But you see how it goes lean, and it goes full lean down here, all the way down to 0. And then we see how we got a lean. It's still kind of going up and down. So it was a little up, a little down on that AF sensor. So it is reacting very minutely to the different amounts of oxygen that are in. And then we see eventually my long-term fuel trim just peaks out at 35%, positive 35%. And then when we reattach the hose, you can see it goes very quickly back down to rich. Takes a little bit longer for the rear sensor to react. And then it comes down here, and then my fuel trims actually go negative to -4 for a bit. And then it takes the long-term fuel trim a little bit more time to react as well. So everything, that's a healthy running car. That's the way it's supposed to look when everything kind of reacts the way it does. The front sensor should react first. Short-term fuel trim should react to the front sensor. And then the rear sensor is going to take a little while because of the distance. And then the long-term fuel trim is going to take longer because of how the fuel mapping table stuff. Another difference, like I said, between the two sensors is one's going to operate at 1200 degrees. The other one's about 640 degrees. So the temperature is very critical. So a special pulse width controlled heater circuit is often used for precise heater control on those new circuits. And one example where we'd find that would be on GM vehicles. I know I talk about this a lot, but it still, even every time I talk about it, I still get people that didn't know that this was a thing. So on 06 and newer GM vehicles, pretty much any of them, 06 and newer. So we're looking at what? A long time. 18 years? 18 years now, yeah. So 18 years worth of vehicles, and still to this day. This is in the this is right in the service information. Heated oxygen sensor resistance learn reset caution. Replacing a heated oxygen sensor, perform the following: a code clear with the scan tool, regardless of whether or not a DTC is set. So it just wants you to basically just reset all the readiness monitors, really. Oxygen sensor heater reset, resistance learn reset with a scan tool where available. Perform the above in order to reset the oxygen sensor resistance learn value and avoid possible oxygen sensor failure. So what happens is it has a resistance compensating circuit in there. As the oxygen sensor heater ages by heating up and cooling off and heating up and cooling off and heating up and cooling off, the resistance is going to increase in that circuit across the plates. So to compensate for that and get the temperature up to where it needs to be, it will increase the amount of pulse width going to that heater circuit to keep the temperature where it needs to be. Eventually, that sensor is going to fail. When that sensor fails, it's going to have much lower resistance around here. But it's going to be fed current, should be around here. So if I over current something, what usually happens? All the smoke comes out, right? So we've had people tell us, oh yeah, I replaced 3, 4, 5 sensors before I figured out what I needed to do. And all you needed to do is a simple reset. You go in under a reset functional test. You click that little button up there that says reset. And it says it resets. And it's done. Now, other manufacturers are like this too. Now, Nissan has a heater circuit, and it also has some compensation in there, but they don't call it the same thing that GM was, because, you know, why would they? So in this case, it's going to be a mixture ratio self-learning that you need to reset. So this function allows mixture ratio self-learning control value to be cleared. Improper uses of this function may cause poor drivability when the ECM self-learning is complete. So you come in here, it's going to tell you your air-fuel ratio, alpha on both, and then you would just simply hit continue to reset, and it would reset it back to whatever the factory specs is, and then it can learn the parameters of the new air-fuel ratio sensors. We can also use our oxygen sensors and air-fuel ratio sensors to test catalyst efficiency. This is a common problem across the board in the industry, is bad cats, or cats going bad, or is the cat about to go bad type of thing. And a cat's not cheap. So our customers want to know, is it going bad or is it something else? Because a P0420 code could be caused by other things. Usually it's a bad cat, but not always. So not going to really go through in depth how the chemistry inside a catalytic converter works, but bad stuff goes in, less bad stuff goes out, basically. The reduction chamber separates the oxygen from NOx in the CO and reduces NOx and creates CO2. Oxidation chamber bonds the hydrocarbons and carbon monoxide molecules with oxygen to form water and carbon dioxide and nitrogen, which is plant fertilizer. So bad stuff in, less bad stuff out. CO2 is still kind of bad, but that's better than what was coming. Don't hear about acid rain as much anymore. So how I'm going to test a cat using oxygen sensor, AF sensor data. I'm going to pull up my data stream. And what I want to see, and this is only going to work on a car that's got a front and a rear. And it's only going to work, well, actually, if we have multiple rears, that's okay too. And multiple fronts, that's okay too. But you can really only diagnose so many at once, but just bear with me. I need a front and a rear on each side. And then I also want to look at throttle angle in this case and vehicle speed. So what I want to do is I want to take my front and rear sensor. So here's my front air fuel ratio sensor. There's my rear oxygen sensor. That rear oxygen sensor is running on the rich side. That is normal. I know sometimes when I explain this, I misspeak and I reconfigure it in my head, but it is normal for it to run on the higher side behind the cat, because that means the cat's doing its job. It's using up all the extra free oxygen that's there, and there's very little oxygen left over after the reaction. That's what we want to see. So it's running fairly flat. We see the front AF sensor is running fairly flat as well. I wanted to make sure I was doing a steady throttle angle, and you want to do a steady speed for a couple minutes. So as I'm doing this road test, you see I get up to about 50 miles an hour. You want to be about 45, 50 miles an hour, something like that, on a nice, fairly straight road, fairly straight, fairly flat throttle input. Front AF sensor wants to be fairly flat. That means my engine is running properly and the mixture is good and is barely adjusting. It doesn't really need to. That's good. And then the rear oxygen sensor must be flat or really darn close to flat. If it is not running flat, that means your cat's not working. If it's going up and down and all around like that, that means your cat's not working. It's just letting through whatever was coming in the front, coming out the back. Basically like an open cat. So you would not see a flat line if it's not working properly. So this is a good cat right now, driving down the road. This is super simple test to do. It works with pretty much any vehicle that has a front and rear oxygen sensor. If you have 5 oxygen sensors, like on some Subarus I worked on, we had 2 in the front, 2 behind the front cat, and then 1 behind the rear cat as well. You just have to figure out which cat you want to diagnose. I do 1 at a time just to kind of see, do the left side, do the right side. But you can do this with pretty much any vehicle. You just got to go out on a road test, record it, and then watch your results back. You can see one side move and the other side not. That means it's got 1 bad cat, right? So it's pretty simple to do. Only takes a few minutes. You want to make sure the vehicle's warmed up, of course. Drive with steady throttle, about 45 to 50 miles an hour for a minute or two. Doesn't take that long. And then just make sure it's flat. Now, another thing we can do with this test as well, with the same data, is when you're done coasting or done cruising, let off 100%. And what do most cars do nowadays when you let off the throttle all the way? It's going to go into fuel cut, and it's going to go to full lean. So when I did that, you'll see the front sensor goes lean first, and it goes to full lean. And then you see the rear sensor takes a little while, and then it goes to full lean there. Like I said, takes a little while and goes to there. So we want to see that, because the front sensor's in the front, the rear sensor's in the rear. We got a distance to cover. It should react differently. Now, if the front sensor reacts after the rear sensor, then I know I got a lazy front sensor. It's not reacting fast enough. Remember how I said we had that ramp time that we needed to worry about, that some manufacturers publish and some manufacturers don't. So if it does, if I lift my throttle and my rear reacts before the front, got a problem with the front. It's not reacting fast. A couple little things to look out for, a couple little tips and tricks that might help you along there. So let's look live on the tool and see what we can see. Gotta reconnect here. There we go. All right, just going to walk you through a couple little things on the couple different vehicles we talked about. Let's do a GM vehicle. We'll do the Acadia. We'll go to scanner. And this is a 2019 Acadia. Now, if I wanted to find that oxygen sensor reset, there's 2 places I can go. First place, I could go into the engine, and I can go into functional tests. And then I need to look, well, where is it? It is not listed as one of the main tests. And sometimes it can be difficult to find some tests. So let's go into output controls and see if it's in there. So we look in there and we go down in output controls, and there it is, heated oxygen sensor heater learn. So if you didn't know to look in there, you might not think the vehicle had it, because sometimes the manufacturers put things in weird places. But there it is right there. I go to my heater learn. On the next screen, select reset to initiate the reset, and select exit or select exit to complete the procedure. Continue. It's going to give us our data, whatever the current flow is right now. And of course, in this case, I'm simulated, so it's 0. But what we're going to do when we hit reset, it's going to reset all of them back to factory, and then they will learn. So if I only replace one sensor, it's still going to reset them all, but then it'll just bring them back to wherever they were before. So you just got to take it on a little bit of a road test. They'll adjust. Reset completed successfully. Hit exit. You're done. Alternatively, instead of trying to find stuff and looking all over the place trying to find it, if you have a tool that has the service resets and relearns menu, which is going to be VerisEdge, any of the Zeus, any of the Apollo, any of the Triton tools, anything with Fast Track Intelligent Diagnostics or the VerisEdge with current subscription on it. We'll have the service resets and relearns quick menu, and this is based on a job. So if I go in and I say I replace the oxygen sensor, or I need to relearn my oxygen sensor, I can just go in here. And then it's going to give me, some top repairs data, TSBs. If I go into functional resets, it's going to pull up any functional tests plus that heater learn. So I go in there. It's going to give me the exact same thing. It's going to pull it out of the ECM, and then I'm going to be able to do it. Right, so that's a lot easier to find stuff. Sometimes if you're having a struggle trying to find it in the actual module, or maybe it lives in a different module. That could be too. Manufacturers put functional tests and bidirectional controls in different places, depending on what they feel like that day, it seems. So if I can't find it, maybe I go in here and maybe I find it there. Makes it a little easier. Let's go into the Nissan now. We talked about that. Be a little bit different because it's a reset for the learning control. So if I go in here, in this case, it'd be down to, we can do engine adaptives. I think we do fuel trim at 2. I think it works for both ways. Let's go to adaptives. And see what it comes up with. Self-learning control, there it is. So I can go to self-learning control. It's going to go through. Allows mixture ratio self-learning control to be cleared. Continue. Key on engine off. Transmission to park or neutral. And see what the values are. Continue. And then it just resets it. Resets it back to 0. Right, easy enough. Let me see if that is also in the fuel trims. It should be. Do the same selections we did before. Oh, nothing available on that. So that wouldn't be available on some vehicles. That wouldn't be available on this engine and stop. So you actually wouldn't even see that if it wasn't a simulator. Engine though, we can go in here and we should be able to find that self-learning control if I don't have the quick menu. So once again, is that a special function? Is that an actuator test? Let's go into special functions and see. It's not an alphabetical order either. There's self-learning control right there. So it's a special function. Right? So it would be the same thing available in there. So multiple ways to find them. It's not like we lock you out if this menu grays out, because there's a lot of people say, oh, my menu grayed out. Well, that's because you don't have an active subscription or an active Wi-Fi connection or things like that. So if that menu is grayed out, you can still go in the individual modules and find it. It's not locked out, but that might gray out. All right, so that is oxygen sensor. Let's talk about what we're going to talk about next week. And next week, we'll be live again, and we are going with OEM-specific training for Mercedes. We've been going through our OEM-specific training all year. We've gotten through the majority of the major makes anyways. We've got a few more to go and then towards the end of the year, but we will be doing Mercedes. So we're going to be talking about what is unique about them. What are some tips from a tech, my favorite section of that. See what other techs have done in those cases. So a lot of good information if you work on those, or maybe if you're not, especially if you're not familiar with them, I think, because that'll give you a lot of that insider information that you don't always necessarily get otherwise. So same time, same place as always, 6 and 9 Eastern. If you want to join on Zoom, go to snapon.com/OT and register there. Otherwise, the 6 p.m. class, like we're doing right now, goes live to our YouTube channel, youtube.com/SnapOnDiagnostics. If you are watching on YouTube, please make sure you like and subscribe. All those good things, because the algorithm's killing us right now. So the more subscribers we have, the better it'll be. Every time they change the algorithm, it takes a little bit of time to adjust. So the more subscribers, the better. And then the 9 p.m. Eastern class goes to my Facebook page. So it's facebook.com/SnapOnJason. Go give me a follow over there. If you want to see any of our other classes in this series, like I said, the best thing to do is be subscribed to our YouTube channel. But you don't have to be subscribed to watch them. Don't think you have to. And it doesn't cost you anything to be subscribed except for a click of a button. So might as well. All you got to do is scan that QR code with your phone. It'll bring you right to the page and it'll automatically subscribe you as well. We have 95 episodes. Episode 100 is coming in like 8 weeks, 7 weeks, something like that. So we will get that, and we are doing something special. So everywhere from intro to ADAS all the way to modern ignition system testing and everything in between, we will do that. So make sure you check those out once again on YouTube, youtube.com/SnapOnDiagnostics. Also, do we have your email address? Does Snap-on Diagnostics have your email address? Maybe we do, maybe we don't. I would say most likely we probably don't. Judging by how many people have scan tools out there and how many email addresses we have, there's a big discrepancy between there. So you are missing out, though. If we don't have your email address, you will be missing out on technical focus articles, technical content, blog quick tips articles, new product releases as well. Plus, they release my schedule, in advance, so you know what that is. So all that good stuff is available right to your email. It's not we spam you, maybe 1 or 2 emails a week. It's not that many. Here's an example of like a technical focus article on timing chains, stretch timing chains. So how do we diagnose that? That's a pretty common problem out there. So a lot of good, valuable information on that. And it's quick little articles, quick tips, that sort of thing. So if we don't have your email address, just scan that QR code and it'll bring you to a form you can fill out, and that'll get you your email. Otherwise, when you go to buy a Snap-on scan tool, make sure your franchisee has your email address before they activate it, and then you'll automatically get added into the chain as well. So. All right, now it's time for questions. But before I do want to mention, if you did join late on Zoom, if you do have a question, just find that little Q&A box, wherever it is, top or bottom of your screen. Type in your question there. I'll get to those in a second. If you're watching on YouTube, just type it in the chat, and I'll get to those in a second as well. But before I do, I want to make sure I mention my buddy Keith, who also does free diagnostics training 2 nights a week. Wednesday is on Zeus and Zeus Plus. Thursday is on Apollo and Triton Tools. 7:30 Eastern, 6:30 Central. Go to snapon.com/OT to register. It is Zoom only, and it's kind of made to be have your tool in front of you, follow along with what Keith's doing on his screen, and do it on your screen type of thing. He's been around for over 30 years with Snap-on, so he actually came over with Sun. So he's been with us for a very, very long time, very knowledgeable when it comes to Snap-on scan tools. So definitely worth your time to check him out. They're all about an hour and a half, 2 hours long. Kind of depends on the tool and the topic and what he's talking about that night. But usually it's about an hour for the first half of the class. It takes about a 5-minute break, and that's all scanner functions, setup functions the first hour. Then it takes like a 5-minute break and goes through all the scope functions on the tool the back half of the class. So very thorough, kind of a really good introduction to your tools. So check that out. All right, let's get to questions. Got a couple on Zoom here. Let's see what we got. John Broham says, what year did AF sensors become standard? I am not sure, but it was a while ago. I'm trying to think. I mean, we even had AF sensors back in Subaru days in like late 90s Outbacks. And they failed all the time. I remember. That's why I remember that, because they used to fail all the time when you replaced them. Like, you replace like 10 of them a day. It's ridiculous. So it was at least in the late 90s. Probably the OBD2-ish era. OBD1, you could get away with the, the single wire stuff. So I'd say, probably late 90s, early 2000s. Let's see. Jacob Lawless. This is a long question, so I'm just reading through it before I say anything about it. There you go. So there's a good example of why you need good reference there. So Jacob Lawless chimes in, says, like always, very thorough. Fun diagnostic topic. Had a few trucks from BNSF, so that's Railroad, come in with oxygen sensor issues. These trucks usually come in very dirty, but this time around they had a big power wash. Found out after they were on the lift It was struggling that after the lift was struggling that the trucks were plumb full of mud, cake full of mud underneath. Mud made its way into the reference oxygen of the oxygen sensors, giving inaccurate readings. So there you go. That's why if it gets damaged, gets crimped, if it gets mud in there in this case, that's where you can have that problem with the oxygen sensor. And it's not actually the sensor that's bad. It's actually just getting a bad reading because it's full of crud. Excellent addition to that. Thank you, Jake, very much. Let's go to YouTube. Nick's checking in from the UK. It is late over there. Nick, go to bed. It is time for bed. I know I'm a night owl too, so definitely thanks for always attending and thanks for your comments. Let's see. Stephen Boyer asks on YouTube, ever seen a P1134 on a Subaru Impreza before? That's a darn good question. Off the top of my head, I don't know which one that is, so let's take a quick look. Just gonna go to shop key real quick. I don't know, 16 Impreza, something like that might be in there. All gonna be the same anyways. Matter, they're all gonna have the same engine. This might be too new though, but let's see. P1134. Does that come back? No, of course not. So I need a year on that. Apparently I picked too new one. Let me see if it's an older one. Come on. Look at 9. Press That's ringing a bell. There we go. 1134. So that is air fuel sensor microcomputer problem. So this is actually kind of a fun description because this talks about exactly what I talked about in here. So the sensor contains a pumping cell and a reference cell separated by a porous diffusion gap. Close enough. 2006, 2009. Yeah, that's pretty close. The purpose of the pumping cell is allow oxygen ions into or out of the reference cell depending on demand. The reference cell must be kept at a landed value of 1, and the ECU supplies the pumping cell with a current, so the sensor output voltage from the reference stays constant. Reference cell is lean and positive current is used to pump oxygen out of the cell. When it's rich, negative current used to pump oxygen into the cell. So that's basically telling you exactly the same thing that happens. And ECM malfunction in the engine control module may need to be reflashed in that case. So it may or may not be air fuel sensor microcomputer problem. Now you would want to look at that front AF sensor. Because the ones that I was talking about earlier in the late 90s, they actually had a microchip board on the sensor connector itself, and they would fail all the time. Basically, if you ever got a code on any of them, you just replace it. In this case, it almost seems like it may be an ECM malfunction. There are no TSBs on it, but it may need a flash. You might want to just double check and see if there is a flash for that particular problem that for some reason didn't come back. Just double check in here real quick. Maybe it's like a related code. Just check in engine systems. Holy crap, 52. A lot of tech tips. Because they do like different calibrations. That's the thing. Air fuel ratio sensor and oxygen sensor. Yeah. They have multiple oxygen sensors on the vehicles, multiple AF sensors on the vehicles, like I said. Multiple different places. Sometimes they put it before the rear cat, which is fun. It's just like it's not even monitoring the rear cat. And this is telling you different things about whether it's a circuit or whether it's a heater problem, which also to reference, like sensor circuit open. Notice how it doesn't list the 1134 in here, but that is a code that exists on there. So yeah, you absolutely can flash a naturally aspirated computer. They flash whatever computers on pretty much any vehicle. It's just really you're putting factory software on there. So you just need to check for an update to the ECM. So either it needs a reflash or it needs the ECM replaced is what that is indicating to me. So first thing I would do is double check and see if there's a flash file available for that vehicle. Basically, you go into mode 9, you check what calibration file it has. and then you check it against whatever's available on the Subaru. And if the one on Subaru is newer, you can just flash it, and hopefully that fixes the problem. Yeah, Nick says Japanese vehicles use AF sensors 2012, 2013. Yeah, like I said, all the way back in the 90s, we were using AF sensors on Subarus, and that's a Japanese vehicle for sure. So, and then Jay says hello, just checking in. So thank you for checking in there as well. All right. So we got a little bit more detail. Thanks for the question there, Stephen. Always glad to have that little extra color and detail and add to the story, right? So very good. Looks like in this case, we have cleared the big board. So with that, I'd like to say thank you. Thank you very much for attending. Hopefully we learned a little bit more about oxygen sensors, AF sensors, how they work, how to diagnose them, and the like. Hopefully you'll join me next week for Mercedes. So with that, enjoy the rest of your week. Enjoy your weekend. Oh, Steven says he's chiming in from Australia. Well, thanks for that. Thanks for chiming in from Australia. Enjoy the rest of your week. Enjoy your weekend. Have a nice night and take care.